Okay, we're returning to the Algebra 2 notes for section 8.4, and this is page 3. And in the first set of problems here, we're supposed to use logarithms to figure out the value of these expressions, to evaluate each expression. Well, you can see we have a minus sign between two logarithms, which we exchange for a single logarithm with division inside of it. That's the quotient rule. Then I'm going to simply simplify, and 27 divided by 3 is 9. And at this point you have to apply some logic. What exponent, I'm pointing at the logarithm when I say that, what exponent would I put on a base of 3 to make it turn into a 9? Well, it's going to be 3 to the second power equals 9. And if you go around the world with it, you can say 3 to the second power equals 9. Now this can also be typed on your calculator, but try to do it without using your calculator until you get to the checking stage. Alright, on this one here, you're going to take and put that exponent up there, and it's going to look like this. Log base 4 of 4 to the third power plus log base 4 of 16 squared. You can assist with the calculator. It's going to be log base 4 of 64. That's 4 times 4 times 4. And over here, if you take 16 times 16, it simplifies to 256. Okay, so I'm going to, at this point, put these two together, log base 4, and I say 64 times 256. Product rule is being used here. The 256, by the way, is 16 squared. So 16,384. Alright, so let's just experiment with this. Let's go, what exponent do I need on the 4 to make it become that number? Let's try 4 to the 5th power and see if that does it. Nope, that's too small. 4 to the 6th power. Still doesn't do it. Let's try 7th power, and we hit pay dirt there, so that's 7. Of course, you can just type this to get the 7, but try to get as much value as you can out of each problem by learning from it. Okay, we're going to take these powers up. So it's going to be go down here. This would be 100, 10 times 10. And 10 times 10 times 10 is 1,000. Now we're going to, there's a subtraction between these logs, so we're going to go common log of 100 divided if it's a common logarithm, you're doing powers of 10. 10 to the first power would be 10, but we want that to go underground, and so we use, instead of first power, we use a -1 power. Let's see, if 10 to the negative first power is 1/10. Yeah, that works. Okay, so if this had been 100, I would have -2 there, since 10 to the -2 would equal 1 over 100. This one here, we're going to take the 3 up and make an exponent. Four to the third power is 64. So I'm going to put a 64 down there. With a plus sign, you multiply when you consolidate. These two logarithms become one logarithm. And we'll put the product of 1/2 and 64, which is 32. And now you just think about the meaning of this. We're looking for the exponent that you would put on a base of 2 to make it turn into 32. And that would be 2 to the 5th. Gives 32. And you can try different possibilities there. 2 to the 3rd, that's just 8. 2 to the 4th, that'd be 16. And 2 to the 5th, bingo, we hit pay dirt there. Alright, sound intensity. There's 3 problems here with that all use this formula here. The loudness is measured in decibels, and this intensity up here is measured in watts per square meter. These are very small numbers, and this down here is called threshold hearing intensity, And it's the smallest amount of energy that hits the ear, and you'll be able to hear it. And that's always 10 to the negative 12th watts per square meter. So very, very small. A trillionth of a watt per square meter has to hit your eardrum before you can hear a whisper, or rustling leaves is sometimes the expression. Now this is a little different than the previous assignment. You'll see some changes here. What decibel level, we're looking for L, is a sound, hang on, let me get the formula started here, 10 times a common logarithm, where the intensity is 8,000 times the intensity of a whisper. Well, this is the symbol for the intensity of a whisper, so we have 8,000 times that. And then it's over that I0 again. And I0 is this number, but we're not going to be using that information here since this cancels off. And so all you have to do here is type that expression. And you'll see pretty quickly here that this is not hard to do. 10 times the common log of 8,000. Turns out to be about 39 decibels, which is incidentally just a normal quiet conversation. Is what, about 40 decibels, somewhere in that vicinity. Okay, a jet engine has 150 decibels. That's your loudness. This has a 10 over here and a common log on the other side. And they want to find out what this value I over I0 is. What is the ratio of intensity hitting the ear when you're in front of a jet engine compared with a whisper? So we first divide on both sides. And then you take the base that's not even written here, and you go 10 to the 15th power equals that. 10 raised to this 15th power is equal to I over I0. And you get this rather staggering result that the energy hitting your ear when you're in front of a jet engine, and then your ears would presumably give up, is a quadrillion times as much energy as a whisper. 10 to the 15th is an astronomically huge number, a quadrillion. 1,000 trillions, which is a million, million, million. Let me think that through. Let's see, 1 billion times 1,000 is 1 trillion. And if you want that by another 1,000, yeah, it'd be 1 million billions is what it would be. All right, the intensity of sound put out by a vacuum cleaner is 100 million times the sound of a threshold hearing. So it's 100 million times what the energy hitting you when somebody's whispering at you. So 100 million times the threshold hearing, which is I0, and then the formula has another I0 underneath it. You can see that right up here, which then makes this cancel. And if you type all this in, 10 times the common log of 100 million, you get 80 decibels of sound. So that's that for page 3 of the notes.